Hello everyone, this is Stephanie Quigley and this is my Challenge Assessment 3 Conduction Temperature Profile project. For this project I'm given a problem and I'm going to go over some of the things to solve it, which include simplifying the heat conduction equation. I will then identify the boundary conditions, which will then lead to me solving for the temperature distribution, and I will graph that so we can understand the trends that we see. After that, we will change 3 different parameters and analyze how those affect the temperature distribution. And lastly, I will talk about a redesign. This is the problem I'm going to be going over, which is a homogeneous spherical piece of radioactive material. And the first thing I like to do for these types of problems is to find all of my givens. So the first given that I see is that the outer radius is 0.04 meters. We are also told that it is generating heat at a constant rate of 5 times 10 to the 7 watts per meters cubed. We are also told, that the heat being generated is being dissipated to the environment steadily, so that's in steady state. We are also told that the surface temperature of the sphere is 110 degrees Celsius. Finally, we are given the thermal conductivity of the sphere as 15 watts per meters times Kelvin. The next thing we need to do is write down our heat conduction equation. So our original equation shows our heat conduction equation, and we want to be able to simplify that to get to the equation there on the bottom. So to do that, we have to ask ourselves 4 questions, and the first one is this steady state? Yes, we are told that it is steady state. Is there heat generation? Yes, we know that there's heat generation. That would be Q triple prime. I'm sorry, in steady state means that we will cross out this to be 0. Is K constant or variable? K is constant, just right here. And how many dimensions? We are working with 1 dimension, which is R. And when we are we want to know what spherical coordinate system, or what coordinate system we're working in, which is spherical. So now we're going to go to our equation and put in the information that we know. So we know that we have 0 equals, since we are a spherical coordinate system, we will have r squared, we will have 1 over r squared del over del r squared del t over del r plus q triple prime over k. Now I moved k already. I divided it out by k. So we moved k underneath q triple prime, and obviously 0 divided by k is 0. So we just divided that out. Next, we are going to simplify this even further. Just to be aware, this 1 over r squared is a constant, and this r squared is in our derivative. So we can't just get rid of them and cancel that. So we're going to move our r squared. We're going to multiply everything by r squared. So we'll have 0 equals del over del r. We have our r squared, which is in the derivative, so we can't get rid of it yet. Plus r squared q triple prime over k. So now we can simplify this even further, just to write it a better way. Which is exactly what we have here. Now I wrote it differently just so you really understand that that r squared is in the derivative here. And this is my final equation. Next, we need to find our boundary conditions, because this will help us then find our temperature distribution equation from our equation that we just found in the previous slide. So our first condition is specified temperature. We are told that the temperature when R is equal to 0.04 meters, we are at 383 Kelvin. Our second boundary condition is symmetry, which means our dt over dr when R is equal to 0 is 0. And these will come in handy when trying to solve our temperature distribution equation. So first things first, this is our equation that we just had in the previous slide. And just moving variables around to the other side, then we're going to take the integral, and we eventually get this C1. So we need to solve for C1 over there, and we can do that because of the second boundary condition, which is symmetry. So since we know that dt over dr when R equals 0 is 0, dt over dr 0, we're also told that R is equal to 0. So that leaves C1 equal to 0. So we're going to plug that back into our equation here. And then we're going to take another integral, and we get a C2. So for this one, we're able to solve this because we were given the specified temperature boundary condition. So we will plug in our TR, which is 383. And we are given our Q triple prime. We're given our K. And then we need to plug in for R. We have 0.04 meters. That gives us our C2. We plug that right back in, and we get our temperature distribution equation. Then I went ahead and graphed it so we can see the trend that is going on here. And so we have our sphere, and as we increase the radius, our temperature is going down. So our surface temperature on the outside here is lower than our inside, which makes sense. So now that we have our temperature distribution equation, I'm going to change some parameters so we can see how that affects the distribution. So for the first change, I'm going to look at heat generation, which is our Q triple prime. So we have our original one to start with when Q triple prime is equal to 5 times e to the 7th, and then I increase that. We'll get our new equations for each one, and I plotted the distribution for each radius. So taking a look at our graph, we can see the original equation has a lower temperature to start with, which also has our lower heat generation, and it also has a less dramatic change from center to the outer radius. As we increase our last one at 1.1 times 10 to the 8th, we can see that the temperature starts off really high, and it has the most dramatic change getting to that max radius. For the second parameter, I wanted to change the surface temperature of the sphere. So again, we have our original 383 Kelvin, and that again has the lowest temperature to start with, but as I increased the surface temperature, the trend is basically the same. We have the same change in temperature looking at the radius, just starting at a different temperature at the center. So the higher surface temperature, the higher temperature overall we'll see in the distribution. For the last parameter, I wanted to change the thermal conductivity, and our original started at 15. This one's interesting. So actually, the higher we increase our thermal conductivity, the lower our temperature is, and also the least dramatic our change is. So when we had a thermal conductivity of 15, we started way up here at a high temperature and had a more dramatic change getting down to that radius of 0.4 meters. Finally, I wanted to talk about a redesign. So for this redesign, you could lower the heat generation, which means we will have a lower core temperature in general, which we can see up in this first graph. Up in this first graph, the lower the heat generation, the lower the core temperature, which is good because we don't want temperatures to be too high. Also, we want to lower the surface temperature, which will also lower the core temperature in this graph right here, so we can avoid, again, being too high at the core. And finally, we want a higher thermal conductivity. The higher the thermal conductivity, the lower the core temp. So our trend in this graph right here, when K equals 30, we started at a lower temperature than when we started at 15. So that is all. Just to go over it again, we simplified the heat conduction equation. We identified the boundary conditions, which then helped lead us to a temperature distribution equation, and we got to graph that. Once we understood that trend, we changed 3 parameters and analyzed those effects. And lastly, I talked about redesign ideas. Thank you very much for listening.